So yes, essentially, this is the topic of the presentation. Really, it's about trying to make money by exporting stuff from Mars. Like Mars needs an export market. I'm going to explain why, probably as a first thing. So I think Mars has a funding problem. To demonstrate what I mean, I made a little table like this. So splitting up the stages of a Mars colony into like the early stages where it's still like a little outpost, mostly about science, so maybe with 100 or so colonists. The middle stages, so up to maybe 10,000 to 100,000, this kind of thing. And then the late stages. So most people agree that by around 1 million colonists, a Martian colony should be pretty much self-sustaining. And then in the early stages, things like science will provide all the income that you need. It's the middle stages that I worry about. That's where I think Mars has a funding program, where you got tens of thousands of people, so you need enormous amounts of money flowing in and complicated equipment. Every launch window has to come like clockwork to keep building things up. But the ordinary supplies of money and investment that you could probably easily command may start to wane unless we get it right. So the typical things I've seen suggested as sources of money for a Martian colony are as follows on the left-hand side. These are the three big ones I've seen suggested a lot. So we have science, first of all. That's the obvious one. So an astronaut can do the work of, like a space probe or something like this much more efficiently. So you can imagine if you had a small colony with just a few hundred people, them talking to NASA or something directly and saying, like, we can do the work of what your newest space probe was going to do for, like in an hour, but what it was going to take a week doing, we could do that in an hour possibly. Astronauts are way better at some things, taking the best soil samples and so on. We can get those and then send them to you for analysis. The current budget for space exploration for NASA is, on the order of several billion, like planetary exploration. So if we could tap into a bit of that, that's a reasonable source of income. I think in the early stages, that's fine. Towards the middle and late stages, though, expanding that to the tens of billions may be a bit of a difficulty. So I'm not convinced that you can. So we've had other suggestions for how Martians might make money. A popular one, Dr. Robert Zubrin himself has popularized this one. I think it's a good one. That is patents, inventing stuff and then beaming the blueprints for how to build it down to Earth and then having people make it for you. That makes sense. But only in the late term, only when it's already done, when it's already clear that Mars is going to be a thing. In the early to moderate, in the early to mid-term, I'm not sure it's so great because expecting people to make designs that are profitable to the extent of many billions when there's only like a few thousand of them there and they're busy with other things, I think it's a bit of an ask. Certainly, a skeptical investor starting out might question the ability of such people to make enough patents to make money, at least at these stages. Real estate, that is the selling of, like you sell large amounts of land in key locations. That makes sense only when you've already won, only when it's clear that there is going to be a Mars colony there forever. In the early stages, there's a great website that sells acres of land on acres of land on the moon for like $30. I think the going price now is about $30 an acre. So at the early stages, real estate really doesn't work. So then we have some approaches to making money mid-term, perhaps, that stand a chance of working, but generally the situation doesn't look that great. So we have to live off of enormous amounts of investment from the get-go. But of course, there is another way to make money. The oldest sort of industrial way of making money, that's just by manufacturing. There's plenty of things you can make in space that are valuable on Earth or in low Earth orbit. So if you're having space hotels and things like that, if we can build space hotels in the Martian system and bring them to Earth, that could fetch an enormous amount because it's expensive to ship stuff off from Earth's surface. There's also exotic materials and things like that that we could send down to Earth for actual use on Earth. Unfortunately, the current wisdom says basically it's impossible to do this, continuously impossible. There's nothing we could do that would actually make it viable as an option, manufacturing this is. So the purpose of this presentation is to give you a few innovations that we come up with at Nexus Aurora to change this last row to something perhaps more like this. I think that we're looking at this the wrong way, that actually manufacturing should be a mainstay of Martian activity, but you just have to look at it in a different way. So first of all, understanding the problem, why does it cost so much to manufacture stuff on Mars and then send it to Earth for use? Why is it so difficult to do? Well, it's shipping costs that dominate. So I've seen different estimates for this. Obviously, no one knows. There's too many variables, but it's a common estimate, something like $1,000 per kilogram to export to Earth from the Martian surface. Like launching from the Martian surface to Earth is about maybe $1,000 per kilogram. That's the shipping cost. So maybe like 5 orders of magnitude more than on Earth. Well, the basics of economics says you got to have a higher sale price than your costs in order to make a profit. The trouble is, basically nothing we could make in space is going to sell for $1,000 per kilogram. It's too big an ask. So the conventional wisdom says then you can't do it because the shipping costs are so high. Barring like new technologies that are just like the Epstein drive out of the Expanse series or something like that, like a high thrust to weight ratio practical fusion engine, which I have no idea how to make that. That might as well be science fiction. So using technology that we actually have, how could we do this? Well, looking further in, we can break apart the root cause of the high cost. But first of all, actually getting stuff off of Mars requires a large change in velocity, large delta V, something like 6 kilometers per second to get from the surface of Mars to Martian escape velocity, and then to like a Hohmann transfer to take you to Earth. It's the cheapest orbit that will take you from Mars to Earth, or back the other way. It's slow, but cheap. I like that. But it's quite a bit of delta V. And you've also got gravity drag involved there as well. That eats up the extra sort of 500 meters per second on the end of that to get to like 6 kilometers per second. So that translates to an enormous amount of propellant per ton of dry mass. It's like 4 tons of propellant per ton of dry mass, probably of rocket. About that, at least, right? And that's dry mass, not cargo. So in practice, you need maybe something like 100 tons of rocket, 100 tons of spaceship per 50 tons of cargo that you're bringing back to Earth. Starship is a little bit worse than this, but you imagine over 20 or 30 years, you can probably get it to be closer to something like this, right? But then, I mean, that's not very favorable. That's a huge amount of rocket and only a small amount of cargo. What's going on? Well, you need a big rocket because there's a high thrust requirement. You have to get out of Mars's gravity field quickly, otherwise gravity drag eats up all your performance. So you need a lot of engines. Starship has like six Raptors and a lot of plumbing and so on to go with it. But the bigger issue overall is aerobraking. When you get to Earth, you're going extremely fast, maybe 11.5 kilometers per second. You got to slow down to come into do an aerocapture, come into an orbit of some kind. The process of doing that requires heat shielding, like disposable heat tiles. This is the whole stainless steel thing with the new Starship and so on with SpaceX. It pushes up the mass of the rocket and the expense of the rocket as well. So in the end, you're looking at something like 10 tons of methyl, so methane and oxygen, rocket fuel, per 1 ton of payload. And a whole new rocket every time you want to send cargo to Earth. So that's just unworkable. Okay, what do we do about it? Well, to summarize it in a sentence, you can launch from the Martian moons instead. So taking, for instance, Phobos, the closer in of Mars's 2 moons, Phobos and Deimos. Phobos to Earth orbit requires a delta V of only about 2 and a bit kilometers per second, rather than 6 kilometers per second. Since you're already sort of in orbit around Mars, you already have a much higher orbital energy than if you're sitting on its surface where you're not in orbit at all. So you don't have to pay so much in fuel. Now it's more like 0.8 tons of fuel per ton of dry mass. And your rocket can be smaller as well. You can use smaller engines because you can take your time doing this acceleration. Like if you go from here to here, and that's how far you can you're going to get the acceleration that you need. You wouldn't really have that much of a performance hit. But even so, like that's like an hour. Phobos would take probably an hour to travel across that. Its day length is about seven hours in total. So you could do that with very little thrust. So your rocket can be much smaller. So already this massively pushes down the price. We can get to maybe, I think, something like $200 per kilogram. Again, like all the numbers here are approximate, but it's to give an idea, right? It's the ratios of costs that I'm really interested in. So maybe we can get a 5-fold reduction as opposed to the situation from launching from the Martian surface just by switching to the Martian moons and naively launching from them. What's on these moons anyway? So Phobos and Deimos, they don't really get much attention. Everyone's obsessed with the Martian surface, as well they should be. It's a very interesting place to go and the perfect place for a colony. I don't think it's the right place for a factory that sends stuff to Earth. That's my position. But otherwise, Mars obviously should come first. But these things are really weird. Like, we should send something to them. Even if you didn't want to do this stuff, you should still send something to them, because they have a lot of, they're quite mysterious. Like, I mean, they have almost exactly circular orbits, which suggests, like our moon, that they were formed by a colossal impact in Mars's past. You look at Hellas Planitia, like the huge, enormous crater in Mars's surface, so that's quite suggestive. So maybe they formed to something like that. But they have the surface spectra of carbonaceous asteroids from way out in the asteroid belt. So something's not quite right there. We have to send a probe to see, and no one has ever sent anything to them, as far as I'm aware. Like nothing at all. All we have is pictures. So the best explanation I have for what they're like is maybe like apples. Right? It sounds a bit strange, but you imagine a core of Martian soil that composes like the vast majority of them, with a thin skin of carbonaceous material that's sort of floated in from the asteroid belt, similar to a D-type asteroid, which is really far out in the belt, so very carbon rich. And hopefully it's like shale oil carbon, so maybe polycyclic aromatic hydrocarbons, you call it. So you get carbon and a bit of hydrogen there too. That'd be fantastic. So there's likely plenty of carbon available on these things, at least on the surface. And in the as you go further into them, it gets colder and colder. So it's likely there's water in the interior. Maybe it's wishful thinking. I don't know. We have to send something there to find out. But there could well be water down there. If there is, so much the better. If there isn't, it's still okay. But in any case, the vast majority of the material there is rocky stuff. It's probably quite similar to what's on the Martian surface. No one's gone, so we don't know. But almost certainly there's ample quantities of iron, oxygen, calcium, silicon, aluminium, magnesium, probably sulfur. I mean, there's loads of sulfur on the Martian surface. What I've spelled out here is more or less the composition in various amounts of like all rocks in the solar system. Right, apart from like weird cases, the general rock in the solar system is likely to have these sorts of things in it. That's everything you need for basic manufacturing. So if you're going to manufacture, spaceship hulls and things like this, like you imagine enormous arenas for space hotels, waste heat radiators, coolant fluid, anything like this, anything you could expect to manufacture and then sell at low Earth orbit at a profit, you could probably do just with what I've mentioned here. And especially rocket fuel, you need carbon for that, of course, but then there's plenty of oxygen and hydrogen enough. If not for metalox, then certainly enough for methyl acetylene, which is like a hydrogen poor fuel we could use instead. So launching from these moons, then it pushes the price down. It's not quite down enough, but it's much better. But we're only getting started. I think we can do way better even than this. So imagine instead of launching directly from, say, Phobos to Earth, you launch to like a Lagrange point, maybe Lagrange point 1 or Lagrange point 2. It doesn't actually matter that much. They're basically mirror images of each other. So they're very similar. But you fly out to these Lagrange points, they're about 1,000,000 kilometers away, so you're in a highly elliptical orbit. And yes, this is definitely not to scale, but you wouldn't be able to see it if I actually did it to scale, right? So you imagine this much further. The ellipse is much more stretched out. The delta V required to get out to L1, which is kind of like a place where the gravity between the sun and Mars and other factors like orbital angular momentum and so on, they all cancel out, so you can just sort of sit there. The delta V to get there is about 860 meters per second, something like this. Depends what time of year you're going, of course. But once you get there, you can sit in a halo orbit and loiter there for as long as you need to until your launch window comes around. So you could send out payloads to here and then have them loiter. Once your opportunity comes, once the launch window opens up, you then, because inside a halo orbit, like the velocities associated with these things are very, very low. So it's easy to get into them and it's easy to get out of them. You can choose when to go and then cut yourself into an ellipse that goes very, very close to Mars. You do a very close flyby just above the atmosphere. Why? Well, because you imagine falling from 1,000,000 kilometers towards the Martian surface. You end up going crazy fast when you get there. In fact, you probably, well, it depends exactly how far you fall and so on, but you're like a hair's breadth under escape velocity when you get there. So you don't want to hit the atmosphere because then you get dragged, but you end up like almost at escape velocity, in which case all you need is a little nudge to get to like a cheap orbit that takes you back to Earth. So maybe 600 meters per second delta V, something like this, right? Well, then 600 meters per second plus 860 meters per second, plus maybe there's a little extra on the end, but hardly anything to get into those the halo orbits and so on. That's only 1.5 kilometers per second total now. So now it's more like half a ton of fuel per ton of dry mass, so including the rocket as well. And say the rocket's about 50-50 rocket and cargo at this point. Well, that's only 1 ton of fuel overall per ton of cargo. So that's more like $100 per kilogram. That's way better. So this coming from basically having a lower delta V in total. We're cheating. We're using the Oberth effect, which is that rocket engines work better the faster you're going, right? Basically. Unfortunately, that's only half the problem. So using those kinds of orbital tricks, you can send stuff from Mars to Earth really cheaply. But we also, when you get to Earth, you need to aerobrake as well. It's that aerobraking thing again. Making a ship that's good at aerobraking is really hard. So you still need maybe 1 ton of expensive rocket ship for 1 ton of cargo if you're going to do aerocapture when you get to Earth, and you need to. So we need some innovations here as well. This is the last part. If you have this, you can push that price down, hopefully well below $100 per kilogram, at which point it makes sense for anyone who's building something in low Earth orbit, for instance, to buy from us, because it costs maybe, we hope, around $100 per kilogram to send stuff up from Earth when SpaceX Starship is done. This is the typical figure given out. So if it's cheaper to get it from Mars than from Earth's surface, you buy from Mars. And there might be billions that go into space hotels. So we could actually get into that market if we get these innovations done. So what do we need? I think we should design a fully and rapidly reusable aerocapture vehicle, like a good one. What does that mean? How do you do aerocapture well? Well, you don't do it like this. So sort of having an orbit that flies past Earth's atmosphere, and then you do some drag and you fly out into a slightly new orbit. What's wrong with this? Well, you got a limited range of aerobraking. It's only sort of this area, right? But if you got a limited range of aerobraking, it means you have to do all your aerobraking in a short time period, which leads to very high heat loading. And the heat loading, I presume everyone's seen sort of re-entry, it's portrayed in cinema all the time, this kind of thing. You're basically engulfed in a fireball, right? So we expect there's a lot of talk about how to get Starship to survive aerobraking when it comes back from Mars, because it'll be going like maybe 11.5 kilometers per second, so like Mach 35 or something like that, right? You want to extend this as much as possible so that your acceleration is lower as you aerobrake. I suggest firstly the following. What if you use like a closer approach? So this is not like a 3D sort of thing where, you know, this is a path that's slightly closer to us. I mean, as in a path which crashes into the Earth's surface, right? Well, obviously you don't want it to crash, but if you had a path like you picked an orbital path, you can obviously change these quite easily. You pick an orbital path that cuts in so that if you did nothing, you'd crash into the Earth's surface. And then if you have a lifting body and your coefficient of lift is high enough and the total drag is high enough, you can survive it, then you can curve your path around the Earth like this and massively increase the duration of your aerobraking. So if you have a good lifting body, you can massively decrease the costs associated then with aerobraking because you can make the whole thing gentler. So in this case, then we want a lifting body. I think the best you can do is maybe get down the acceleration needed to like a third of a G, something like that. You can't really go much lower than that, but that's still massively better than the, you know, the several G perhaps that's required if you're doing things the traditional way. So that's where we get to this semicycler thing. What's a semicycler? Well, semicycling is a particular orbital style, the second of the two innovations I'm going to show you. But a semicycler itself is a spectacularly good aerobraking system. To do that, you need to have a lifting body that has as low a heat loading as possible. So the only equation I'll show you, I promise. Roughly speaking, the heat loading goes something like this. It doesn't actually go like this. I have no idea what it goes like because I don't have like $10 million and access to cluster supercomputers or a PhD from Oxford. So I can't quite do hypersonic aerodynamics, unfortunately, more's the pity. But it's roughly something like this, right? So where you have sort of watts per square meter of heat shield, the amount of heat that has to be absorbed by your heat shield thing. It goes roughly as, you know, some constant, that's what it is for Earth, times the square root of 2 times the mass of your spaceship divided by the effective radius of your spaceship. So sort of lower density, larger things have a much easier time aerobraking than small things. And then we have v squared on the end. That's what makes this so difficult. The square of 11,500 meters per second is, you know, like a 100 million, right? So that it'll evaporate, you know, no problem, unless you have the right heat shielding and so on. So bigger ships have lower heat loading in general. That's the trick. Hence, I present something like this. I think this is probably the best sort of general idea for a scheme to make a system that's good at aerobraking. So it's around about 100 meters wide, as I see it, but the bigger you make it, the better. I think 100 meters wide is a reasonable start. On the front, you'd use maybe a nickel-based superalloy shell. So with a nickel-based superalloy, because it's an alloy rather than like a ceramic, it's easy to fix in space because you can weld it if you need to make repairs. Hence, maintenance costs are greatly decreased, and there's nothing that gets thrown away every time you use it. You support the thing with a series of inflated structures, right? So pressure stabilized structures. It's like a beach ball. You know, you imagine a beach ball that's heavily inflated. If you try pressing on it very hard, you've got a lot of stiffness there, even though it's a very light structure. So pressure stabilized thin steel structures. You can balance your superalloy shell on top of them, right? And get it stiff enough that it survives. If you're clever about how you design this, you make it as large as possible, and you store your cargo somewhere in here, like right in the middle where it's coldest. Maybe you could get something on the order of this, so like 750 tons for 2,000 tons of cargo. I don't know how to do that for real, but maybe something like that is possible. But in which case, we get much
Philip,
better
I'm sorry to
performance.
interrupt. Just a 5-minute heads up.
Okay, cool. That's fine. So, what's the general plan then? Well, you come in from Mars, like with your Homer transfer orbit as cheap as you can. You do as little aerobraking as possible, just enough to make an aerocapture so that you're captured into an orbit of some kind. The orbit takes you out to Lagrange point 1, or equivalently Lagrange point 2. So you don't have to do that much then to do this, because it's a very high energy orbit. So you're only doing like 500 meters per second, perhaps delta V, to get into aerocapture. You fly out 1.5 million kilometers up to Lagrange point 1, and then you enter a halo orbit again, right? And you can stay there until your next launch window appears and you fly off to Mars the traditional way. But the cargo doesn't. The cargo instead is led out somewhere here, goes into an ellipse, and then passes by Earth again. But when it does a little bit more aerobraking than it did last time. You can only do small amounts if it's just like basically a box with cargo in. You have that fly past Earth and do a couple, a few tens of meters per second, perhaps, aerobraking, and then slowly decrease its orbit. But you can do many such passes, because if it's just unmanned cargo, there's no real time constraint, no serious one. So if it takes a year of small passes to slow down eventually to the low Earth orbit, then that's fine. The real work is done by a sophisticated machine at the start. You front load your aerobraking, and then you do gentle aerobraking afterwards until you get to the end location, like low Earth orbit, where you get to a space hotel under construction. They're like, excellent, more construction materials. That part is cheap. That part is no problem, because you can do it over many passes. You have to aerocapture, however, that is, stop yourself flying off into interplanetary space in one pass. That's why you need a semicycler. So what is semicycling then? Well, that's the second part of this. So when you need to go, you return to a close approach with Earth and you fly off to Mars, just the same way that you got here in the first place with the semicycler. You only need a little bit of a push to get you there. So this is due to Sean Wessels, one of the core members at Nexus Aurora. Fantastic piece of work. This perfectly sort of describes what the general trick I've just told you about really is. That is, you cycle between Mars and Earth in such a way with your reusable aerobraking machine that you're storing up most of its orbital energy in halo orbits at Lagrange points at either side, at Mars and then at Earth. And then jumping between them only takes a little bit of delta V. So maybe a kilometer per second overall. So it massively decreases the cost of bringing your reusable aerobraking material, aerobraking vehicle back. So where does that bring us in terms of the costs of bringing things to Earth? Well, maybe if you got 1 ton of semicycler for 2.5 tons of cargo, my estimate, I haven't actually designed that to the point where I could build one tomorrow, but if you could manage something like this, it only adds around maybe an extra 100 kilograms of propellant per ton of cargo delivered, because you hardly need any delta V to get it back to Mars and switch between Mars and Earth each time. So the total shipping cost can be reduced maybe to like a factor of 20 less than what people thought it was starting from the Martian surface. So now a whole new market has opened up, potentially. I think this works. And hence, Mars can make money by manufacturing, the oldest and best way in the industrial world to make money. And that's it. That's the presentation. Thank you so much for listening, everyone. I'm happy to answer your questions with whatever small time we have left.
Okay, yeah. So we have 1 minute until the next workshops begin, but
yes,
I guess, yeah, I can ask these questions and we can stay a little bit over, and if people want to leave, they can. But so the first question we have here is, I like your ideas on aerocapture. I've been thinking the same. My worry is about satellites in Earth orbit. Satellite internet is placing thousands of satellites in low Earth orbit. Even if we clear debris out of Earth orbit, how do we avoid colliding with satellites?
Right, well, you have obviously plenty of freedom over exactly when you get to Earth. You have plenty of freedom over what angle you come in from. So it's the same kind of problem that would exist for bringing back Starship from Mars, for instance. So whatever solution exists for that will have to exist for us as well. I presume it'd be easy enough to clear out some avenues, perhaps, through which aerobraking can take place safely. But it's a reasonable concern. We'd have to clear out a lot of space junk in the near future. I have some ideas, perhaps, on that as well, but that's for another time. But yeah, other than that, big problem. Much thought needs to go into that. And on my side, I haven't thought enough, I don't think, on that. I don't have any good innovations yet, fortunately.
Okay. So another question. NASA's Ames Research Center developed a new thermal blanket called Draphesy, developed too late for the shuttle, but tested on X-37. The fabric is a synthetic ceramic called Nextel 440. The blanket is covered in inconel foil for aerodynamic smoothing, but for aerobraking, you don't need that. And heat load isn't as great for atmospheric entry. Why not use this fabric?
Okay, so generally speaking, with ceramic materials in general, it's very hard to repair them when they go wrong. That's the major thing. So when you have access to all the infrastructure that we have on Earth, you can use heat towels and things like that with no difficulty. With something like this, my concern is if it starts to degrade. Firstly, with ceramics, you don't get much warning before they just break. Something like steel, it tells you when it has a problem. It's easy enough to see. So with ceramics, it's tempting to go with them, but in practice, they have a lot of downsides. So it seems like the kind of thing that's very difficult to fix in space and to maintain. But of course, you can get much better performance out of ceramics. So my instinct to go with Inconel comes from its steel's very forgiving. Okay, so anything that's like a steel, I will jump on because they have the best sort of combination of material properties. But ceramics can beat them in specific areas, for instance, heat resistance. So if you could get something like that doesn't need careful repairs, or that's easy to repair on site, really, if you get a tear, you need to pull something out, and then if it's a ceramic fabric, do you sew something onto it? That's very difficult to do. Because of course we can't have a matrix material. So ceramic fiber composites on Earth, you've got like a plastic or something like that. Obviously that'll just boil off if it's an aerobraking thing. So my problem with that's probably maintenance. But if it can be demonstrated that you can do that without maintenance issues, then that may well even make this better. So I remain agnostic on the issue, but those are my feelings.
Well, yeah, and that's it for the questions. And thank you, Philip, for your presentation.
Yes, thank you so much to everyone for listening, and thanks for the questions as well. Very insightful stuff. Actually, those are two areas I'll certainly be looking into.
Okay, thanks.